Welcome to Mechanics of Composite Materials. Today we'll be going into more introductory material, more of a summary, and then we'll tackle micromechanics. So composite materials, why they're so important is because we're using them in a lot of different applications for weight savings, and we're also using them to give you higher performance for whatever application you're working on. The problem that we have here is that with composite materials, you may have an issue with cost, and you're going to have issues with long-term sustainability. And that's an important consideration anytime you adopt composites. When you adopt composites for a particular application, remember, there could be the potential that that material can go obsolete. And if it goes obsolete, then now you have to come up with a new program that replaces that material. That happens a lot. For example, in the procurement phase, there's a potential that when you buy composites, you cannot find them from the same manufacturer anymore. Like Torre Fiber, at one point in time, look it up, was having trouble delivering fibers to a lot of people because they had a long-term contract with Boeing that required a lot of fiber. And so for that reason, the suppliers had to go to other locations to buy fiber. So that's something you want to keep in mind with composites, that you may have these disadvantages, these issues that could come up. So what is a composite material? We talked about it before, but I want to make sure it's clear in our heads. The fiber carries 75% to 90% of the load, carries and provides most of the stiffness, provides amazing strength, and it provides thermostability, electrical conductivity, or insulation as well. The matrix material is really there to hold the fibers together and bind them together. Usually it's more ductile, the fiber is more brittle. The matrix tends to be tough, and it's there for a reason. It's there to be able to sustain some impact damage resistance as well, to provide some of that. And we also know that the strength of the matrix is way lower than the fiber, but it provides the shape to the structure. And so when you look at concrete, concrete is a great example. Concrete is actually a very low strength material, but when you reinforce it, it provides quite a bit strength. And the mixture in the concrete is really providing the feeder to keep everything together. And so what? So the matrix and the fiber both provide the best characteristics of each material. The fiberglass, for example, acquires strength from the glass, and the flexibility comes from the polymer material. So I hope those ideas are clear. And and we went through this already. Just to remind you, a structure is going to made a bunch of lamina, which we call laminate, and each lamina is going to have fibers and matrix, as you can see in the top picture there. And then we talked about the various composite materials you could have. The applications we'll be talking in this class will be more focused on laminated composites, but could be widely applicable to other kinds of composites, like particulate composites, fiber reinforced composite, flake composites. And then we talked about the fibers. For fibers, you're going to have several types. You could have a carbon fiber, which starts as a polyacrylonitrile fiber. You have the boron, which is a advanced fiber system, a glass fiber, which is a first synthetic fiber, and it starts as a silica sand, and you have silicon carbide. So these are the typical composites you could have. They all provide different stiffnesses. As you can see here I show the stress strain curve. Carbon fiber has one of the highest stiffnesses, and that's why you're going to see carbon fiber being used quite extensively in aircraft and automotive industry. For matrix materials, you have polymers, metals, and ceramics. And when you combine fibers and matrix, you're getting the full system as a whole. So fibers, let's start with glass, and I want to go through advantages and disadvantages and the types of glass you could have. Fiberglass is the most widely used fiber. The advantage of that is that it's low cost, it's corrosion resistance, but also offers low cost relative to other composites. The real disadvantage here is that it's low strength, and it also provides too much compliance, so high elongation, and it offers moderate strength and weight. As a consequence, you're going to see fiber glass composites being used in surfboards or sporting goods because I don't need the highest performance in the world. It needs to be light enough, it needs to be strong enough. And that balance makes it perfect for this kind of application. So we also got the types of fibers. We have E glass and S glass. S glass tends to be higher strength. Fibers like Aramid, we have Kevlar as, as an example of an Aramid fiber. It's a high performance fiber system. And examples where you may see these Kevlar applications are more protective clothing, industrial, and even sporting goods, because in some applications where you have high impact events, you want to have a Kevlar system because it's very good at high strength and it's also lighter than glass and it's more ductile than carbon. So really good stuff for that. And it's actually used in a lot of protective clothing. Again, the one you're going to see a lot is going to be fiber carbon. The fiber carbon is high stiffness and strength, low density. The properties are pretty nice. You know, they have a range of properties from standard modulus to high modulus system. And you know what is amazing about carbon to me is still is insane to me is that it's 5 to 8 microns only in diameter, and that's smaller than the human hair. So when you board an aircraft, when you're boarding an aircraft or you're looking at a launch vehicle or a spacecraft, we're really talking about here of a composite really made of high performance composite, okay, which has diameter carbon smaller than human hair. So what is providing that strength is really the idea that the strength is in numbers. Like ants. Have you seen ants carry very heavy weight? Well, when you put these fibers together and you put 2,000 of them, 12,000 of them together, right? That's going to provide the greatest strength in a particular toe system. Types of carbon fiber, it varies in strength with the processing, and there's trade offs of strength and modulus that need to be considered. Boron fibers are another type of system. They're high stiffness, very high cost, large diameter, very different from this carbon, which is 5 to 8 microns. Here we have close to 40 times the diameter. Great compression strength as a consequence. Uh, we also have another one called polyethylene. Trade name is spectral fiber. You may see that high strength, extremely lightweight, low range of temperature use. So very nice for low range temperature use. We also have ceramic fibers, like very high temperature applications like composites for engine applications. That's where you're going to see that. And here I like this plot because it shows a comparison of the different systems. And I want you to focus on a very popular one, which is the AS4, which is number 4 here. That's using a lot of research labs around the country. Really high, very, very nice strength, very nice stiffness. When you go to the IM7, which is a high class, composite using aerospace application, very high strength. Look at that, way above everything else out there, very nice stiffness. You go to boron, much higher stiffness, and then you go to graphite, way higher stiffness. But look at the strength, keeps dropping. So so there's trade-offs, and you have to look at your application. You have to look at what you need for your application. Some cases you don't need the strength. What you need is a stiffness, and so you want to balance that during the life of the program. Here, what I show, and this is a great plot, is a table. It shows the tensile strength and tensile modulus across a range of fiber systems. And what you see here, for example, is I have e-glass, which has very low tensile modulus compared to everything else. And then we look at e-glass, how that compares to carbon, for example, in terms of strength, and it's not that off there. It's less, but it's not that off. You also have the fiber density. You can see how the carbon has much lower density than the glass systems. Now the silicon carbide here, very, very high density, so it's heavier by twice than carbon, for example, which makes sense. When you look at this list, it makes sense why we use a lot carbon systems in, say, T300, IM7, S4. We use those in aerospace applications because they provide great uh, low density yet very high strength, which is great for the applications of concern. And the modulus are great as well. So that's what we get there. You can see here, if I were to compare now these fiber systems to steel or aluminum, I can see here that I have 7.87 for steel, and the highest I see here is silicon carbide, 3.19 uh, grams per cc. And so you can see it's double the weight, and then the modulus I'm getting, it's not much better, right? We're seeing here the modulus is 483 for silicon carbide, 207 for steel. And then you can see here the tensile strength 0.38. Look at that. Look at that beauty. Everything here above 1 GPa. GPA not grade point average, but gigapascals. So amazing stuff. Great performance across the board. So going back, E is for electrical, S is for strength, and there are other types of glass. For example, you may have T glass, which is for thermal. R glass is going to be for reinforcement. You're going to see A glass for alkaline and other applications as well. And the idea here, guys, is when you're tailoring a particular system across the board, what you want to do is get the best performance and the best application. For example, if I really want a fiber system to get you the better conductivity, electrical conductivity, then e-glass makes sense. And that's what you want to do. You want to balance cost, okay? You don't want to go crazy just because composite sounds cool and I have a surfboard I want to make. I don't want to go with IM7. Who is going to buy a surfboard that costs like 20,000 grand? Maybe there'll be some that will do that. But you want to be smart about density. You want to look at the weight density. You want to look at the strength performance. And then all that needs to be combined into a package that also makes you profitable. Because the end goal here is profitability. Okay. Maybe some of you may think that some of this is for the environment, but in my experience, environment plays less of a role. Now, I encourage you as a good citizen of this world that you try to also take that into consideration. But from my experience, a lot of the push is going to be performance, performance, profit, profit, profit. And if you want to be a good citizen of the world, you want to consider environmental effects. Of course, I want to do that, but I guarantee you that a lot of these applications, you're going to have to charge people more money. Are they going to really buy? The other thing I want to keep in mind, and I really encourage you, if you're going to pursue this area of expertise, to do some research as well. So if you want to pursue research in this arena, I encourage you to do that. One area that we need more research on is sustainability. We want to be able to come up with materials that are biodegradable, they're able to give you the performance you need, yet Yet, when you're done with the aircraft, I'm done with the aircraft. After 30 years, I'm done. I want that aircraft to be biodegradable. Can we do that? Can we find ways to do that? And so I challenge you as engineers, young engineers, and challenge you, whoever is looking at this, to come up with ways of doing that. And absolutely, we want to do that. But keep in mind that a lot of the applications, short-term implications and applications, are really to try to get the best performance you can with less cost for the most profit. That's really what drives a lot of this stuff. We want to be environmentally friendly, sure, but keep those things in mind as you're working through these ideas, okay? And again, I'm all for the environment. I'm not against the environment. I really want us to do the best we can, but we need to figure that out, right, as a society. So we have a lamina with unidirectional fibers. And what I mean with the unidirectional fibers, the fibers are running one direction, as you can see here. Then we have lamina with woven fibers. So fibers going in one direction and also in the other direction. Now it sounds very strange, but the warp direction tends to be the straight fiber, and the field direction tends to be the one that goes one up, one down, one up, one down. So something to really keep in mind as you're working through this can get confusing. So unidirectional fibers, fibers going along one direction. Woven fibers, I have fibers going in two directions. Actually, can go up to three directions. I'll show you an example later. A composite laminate is more than two plies. If you see a sandwich structure, you can have two kinds. You can have two kinds. You can have an aluminum core as one example, and you can have foam core as another example. Which one you select is going to be up to the application. For example, in aircraft applications, if I select an aluminum core for the tail, what's going to happen is that aluminum could get corroded. So maybe you want to do something, select a different aluminum that's more resistant to corrosion. The foam, for example, is a material that can absorb a lot of moisture and it can have strength reduction as a consequence. Foam core may not be good at very cold temperatures, it can start cracking. It could be quite degraded at very hot temperatures. You want to look at all these factors as you work through this because it's not straightforward to just say I want one or the other. There's other kinds of core materials like Nomex and many other kind of applications. Now, why composite sandwich structures versus a laminate? Let's think about that question very carefully. A sandwich structure, as an example, can take very nice bending loads, right? Because I put two faces apart far enough, and in between I put core material. The face sheet is going to take the majority of the load while the core is providing the bending resistance. So you're going to see a lot of applications in aircraft, say for example, you have a core used in the tail, but the fascias are fairly thin. Now you'll be surprised just by putting the fascias apart so much, I'm increasing the bending moment of inertia. If you recall back in mechanics of materials, you learned that the inertia, I can put air in between two strong materials and I'm increasing the bending resistance. Obviously, I'm not going to put air because air, I need something to bind stuff together. But even if I took, and I'm telling you, foam, I'm talking about foam here. Foam can be used in aerospace applications. And if you give me a second, because I have to. So now I'm going to continue here explaining that you have to look at the application of foam core and aluminum to determine what's the better application for the actual, whether it's aerospace application or is an automotive application. Does that make sense? I mean, for composite materials, then I have also the fact that I have unidirectional composites. I have textile composites. And I already talked about this one here. We have random short fibers. We can have continuous fibers. We can have plain weave, which I just talked about. We can have triaxially weave fibers. So you can have fibers going in three directions. And then you have the biplane weave, which also have several fibers going in various directions. But generally speaking, the composites you're going to see the most in a lot of the applications are going to be continuous fibers, plain weave, these kinds of fibers. And when I say woven here, what I really mean is two systems of yarns interlaced at right angles to create a single layer. While for braided, we're talking about a series of intertwined spiral yarns, okay? So here you can see a plain weave composite. A plain weave has one up, one down, one up, one down, one up. And as I said before, these straight ones are called the warp, while these tend to be the fill. It provides fabric integrity. It applies dimensional stability. While a 2x2 twill uh, also provides even more drippability. And that when I say 2x2 twill, what I'm talking about there now is I have one down, two over, one, two down, two over, and so forth. I'm sorry, two up, two down, and that's what I mean with 2x2 twill. When I talk about satin fiber harness, great for drippability as well, smoother surface, improved translation fiber properties. And what I'm talking about there when I say satin harness is going to be four up, one down, four up, one down, and that's that five can be confusing, but we're really talking about four up, one down. So if I say eight harness setting is going to be seven up, one down, and so forth. So keep that in mind. If I give you a piece of composites, you can tell if it's a plain weave versus a setting harness. You can see from the surface finish. This is going to have a way smoother surface finish compared to a plain weave, for example. More rough there. Braided composites. So you have diamond braid, you have regular braid, you have Hercules braid, you have trax lead braid. So you can have various braided types of composites being considered. Woven composites, here's 2 by 1 twill, 2 down, 1 up, 2 by 2 twill, 2 up, 2 down, 2 by 2 basket. That's basically on in two directions. This is what's happening. You have the craft foot satin, 1 down, 3 up. A 5 harness satins. These are the ones I just covered just a minute ago. And you have more and more drippability uh, when you have these situations. These ones can provide lower strength, for example, because now you have more undulations. And so that can cause stress concentrations in the fiber. Okay, so we continue on. We look at composite material versus metals. We have specific strength versus specific modulus. And in this case, you can see here how, and I created this, and I like it. It shows the fiberglass over here compared to metals. You can see quickly how the specific modulus has dropped. So I'm not getting a lot of performance out of the modulus, specific modulus, pound per pound, um, compared to metals. In terms of strength, clearly is in the ballpark as metals. And then for composite materials, look at that. Greater performance overall compared to metals in terms of modulus and strength. And we covered this picture already once. The point I want to make in this picture is very specific to one thing I want to point out because I covered already this in a lot of different flavors. But the main point I want to make is if you select a composite structure and use a standard quasi-isotropic material, which is 0 plus minus 4090 symmetric. So 0 plus minus 4090 symmetric is your quasi-iso. I want you to look at a specific strength here, uh, not too shabby, right, compared to steel and aluminum. So specific modulus, not that, not I will not call that amazingly better. Look at the ultimate strength. Okay, ultimate strength, in the same ballpark as aluminum. Young modulus, same ballpark. Yeah, it's lighter, but I'm not seeing a huge increase in performance other than a little bit decreased weight. So yeah, quasi ISO can give you good advantage there, but keep that in mind that you can tailor them to get even better performance. Maybe, and I'll teach you how to optimize and tailor composites to get the best performance. But the best performance may not be your standard 0 plus minus 4090, 0 plus minus 4590 symmetric. That might not be the best option. For example, in a pressure vessel design, a 0 plus minus 4590 may not make sense because I have a lot of hoop stress, which maybe hoop plies make sense, 90 degrees alone. And then I have a significant axial load, which is basically half of the hoop. And so I want to also consider that in the assessment. When I look at composite materials versus metals, the advantages is high strength, high stiffness, tailored design, fatigue life, dimension stability, corrosion resistance, low thermal expansion. Here I can see a fatigue curve, and the fatigue curve compares the fatigue of composites versus aluminum. Clearly here you can see the increase in life for the same stress. Disadvantages, manufacturing variability and defects, complex mechanical characterization, complicated repair of composite structures, degradation of structural properties under moisture and temperature, poor energy absorption, and impact damage. So that's a disadvantage. You're going to have a much more harder time getting a full characterization test. It's going to be harder to repair. That's very well known. It's going to degrade much easier when subject to moisture and temperature. And under impact damage, you could have issues there. They can be expensive and very complex to inspect. And again, a lot of manufacturing variability needs to be considered. When I look at failure modes of composites, we have fiber breakage. And fiber breakage means the fibers are breaking apart. We have delamination, which is ply separation. You can see here two ply separated, matrix cracking, which is cracking of that matrix. Here you can see ply lifting and crushing. Okay, so the other thing I want to point out is that the failure modes in composite materials for laminated composites are quite complex. You could also have fiber to matrix debonding. The fiber can come apart from the matrix. That debond can come apart. You could have crushing at the hole. So, for example, the bolt here is pushing against the fibers, buckling them. I could call that micro buckling, for example, of those fibers. You could have ply lifting, where the fibers are getting lifted by that shaft pushing against the circular hole. So when we look at the failure modes of composite sandwich structures now, instead, what we have here is a number of failure modes. And we show them here on the right-hand side. So let me start with phase sheet failure. Phase sheet failure is going to be any of these failure modes that occurred in the lamina, but is occurring here in the phase sheet, because phase sheets will be made of lamina, for example, in a lot of applications. Then you have core shear failure, where the core cracks. Okay, that's one possibility. You also have phase sheet wrinkling and core crushing. So here you can see the phase sheet has wrinkled and crushed. Okay, and then we have buckling and delamination. And then we have shear crimpling. We have shear crimpling, which in this case, there's eccentric loading that's causing the crimpling there. And then we have phase sheet dimpling. And then intercellular buckling. Okay, so intercellular buckling means, for example, take a honeycomb structure. A honeycomb structure is going to have a phase sheet that's unsupported between the empty cells. And so now the phase sheet could potentially buckle in between the cell walls. So that's what we're talking about there. And these ones here, these four here, really talk to instability phenomena due to compression loads. These are what these four are. And in general, shear crimpling is an instability failure mode. This one right here, I want to cover a little bit more. So that one occurs largely when you have out of plane deformation. Let's say if you have a buckling event, that's where this could happen, for example. And then there's other failure modes that I did not cover here, such as, for example, core indentation. So if you have out of plane concentrated loads, so you have an attachment here, an attachment right there. The attachment can push a concentrated load into the fitting corner joints, and I will show that in a case study later in an actual application. And that can be avoided by spreading the load over a larger area. So if I have an attachment, I want to make sure I know what I'm doing with that attachment carefully. Okay. We also have, um, I want to cover also a little more the phase sheet wrinkling that I talked about. So phase sheet wrinkling, which you see here, is the potential for in-plane compression load to be so severe that it pushes the core down. It crushes the core, and buckling then occurs as a consequence. So these are the failure modes. Again, a lot more complicated for sandwich structures, a lot more to consider. And then you have the laminates failure modes. And these failure modes are going to be part of this set of failure modes. So not only you have these failure modes, you also have all these failure modes to take care of. Okay, and in this course, we're going to cover how to predict these failure modes and how to assess them for a particular design. So then we talked about manufacturing already quite a bit. We talked about, you have pre-preg, you have the tooling, and then you put everything together in a layup, you vacuum bag it, and then you cure it in an autoclave. And then you have your final product, which should be inspected and verified for no manufacturing defects. We also talked about the different components that go into making a composite from bottom to top. And in general, what we talked about is that we need some release material. We need a tooling where we can stack the composite against. We need a dam that prevents epoxy from, or the resin from flowing out uncontrollably. And then we have the breather materials to cause the vacuum to disperse more uniformly. We talked about the bleeder material to absorb any excess resin and promote resin flow. We talked about making sure we have a peel ply that provides the laminate with the surface texture that we need. And finally, we talked about a vacuum bagging process that allows you to pull vacuum successfully using this double side tape with this pressure valve. And now you connect that to the autoclave and pull vacuum, put that in the thermal vacuum chamber. Um, and, sorry, in the thermal chamber, the autoclave, and then apply the pressure required to achieve what we want to achieve. And the vacuum here, what it's doing is helping us uh, compact the part, so remove any voids, and the autoclave then will provide the extra pressure needed to even push any other voids out. And we talked about how autoclave is basically the part is getting cured outside of the oven and no pressure is applied. And then here's a zoomed in view of the things we discussed. So this is more of a summary. This is laying up of composites. You can see here foam structures getting um, put on top of a face sheet. And on top of the face sheet, there's a film adhesive. I don't know if you can see the white part, that's a adhesive. And you can see these dams made of cork, which are meant to do exactly what we talked about, which is to prevent resin from flowing out uncontrollably. Once you put the cord down, you put the face sheet next, the top face sheet down, and then you're gonna have these areas that we have to apply a roller. You want to pressure it so it's like glued down nicely, and you do that with a roller, like if you're painting a wall. That's gonna try. You're gonna try to remove any voids you can in that process, and that's the picture I was showing here. This hand roller is helping with that process. So here as well, we take a roller and push any voids out the best we can, right? All we can do is hope the best. Be very careful in this whole process. And then we put this in the autoclave, running through a profile that has been predetermined by a lot of studies, either by provided by the supplier of the materials, or you received them from the supplier. And now you're verifying that the performance of the materials are up to par using the curing cycle. Once done, we cut it up. And once cut it up, we can inspect them first, or we can inspect them at this point in time. So curing, what is the curing process? So I want to I talked about it before. I didn't cover stage A, stage B, stage C, stage C, stage D in carefulness. So I want to do that a little bit now. Um, but curing is drying and hardening of the resin matrix of a finished composite. This may be done unaided or applying heat, typically up to 100 psi, with a temperature application of 250 to 390. Okay. Layup is the process of arranging those lamina into a laminate to make the desired part. We'll come back to that point a little bit later today. Stage A is basically when you receive the materials in the basic form, in the raw state. Matrix is in liquid form for thermoset resin or in granular form in thermoplastics. Very important to consider that. So the matrix is in liquid form for thermoresin or in granular form for thermoplastics. But stage A is the materials in the basic form. Stage B, or B staging, is when the fibers and resin have been combined together into a single layer, and the thermoset matrix composite appears semi-liquid so the sheet can hold the shape. For thermoplastics, the matrix is solidified, In stage C, the layers in stage B are stacked to make flat plate laminates. In stage D, final product configuration is formed. We talked about filament winding. I won't cover this again. And we looked at how filament winding works. We talked about fiber placements and how fiber placements work in a very nice way where the toes are fed into a heater. And then it already has a compaction roller right there. And then as the fiber is being put down, you're rolling it and you're getting the highest compaction possible. We talked about resin transfer molding, although I want to talk about it a little bit more today. In resin transfer molding, you have a preform. So you have a reinforcement assembly that forms the skeleton of the structure, and you put in your tooling. The mold then is designed to provide for resin injection venting and is there to optimize the resin flow. So once you have that, you have the injection process to occur now, and the resin metering, mixing, and heating and injection occurs. From that point on, you go to now the curing process, which is going to be a prescribed time temperature cure cycle, and then finally you demold it. This is used a lot in automotive cars, high volume productions where you're going to see that of complex thick parts. Dry fiber reinforcement is shipped into the place mold. The mold is then designed to allow for the injection of that resin. And during injection, the resin hardener are metered, mixed, and heated and injected at pressure into a closed mold. And then after completion of the mold filling, the temperature cure cycle is completed. Um, you have the part done. And now all you have to do is demold it. Um, I won't go into more detail other than saying rich and transfer molding is great for high volume production. We also talked about compression molding a little bit as well, where the molding material is preheated. So now the molding materials are one preheated and placed in the heated mold cavity. The mold is then closed, the pressure is applied, and the material that's into contact with the mold area is getting heated as a consequence. Heat and pressure are maintained until the molding material has cured, and basically you're going to have the product at the end. Advanced composite thermoplastics are usually the ones compression molded, and you can use all kinds of materials, fiber architectures like unidirectionals, woven composites, randomly oriented fibers. I've seen that used. I've seen chopped strand and randomly oriented fibers used for these applications. So, laminate nomenclature. I think this is going to be very important as we move forward. When I give you the first, I'm going to give you something called a stacking sequence. Okay. The stacking sequence is going to have a bracket. A bracket is used. For example, I'm going to use a bracket. Um, let's see. Works. So I have a bracket here. And that bracket is going to represent the opening of that stacking sequence. And when I say stacking sequence, I mean I'm going to provide you with the lamina orientation and what plies go where in that stacking sequence. So think of a big stack. I'm going to tell you how that lamina works. And so that's all we're trying to say here. You can see here the first one that we have is 45. And that one is the first one that goes against the tooling. So if there's a tooling surface, this first one usually goes against the tooling. That's the typical convention we use. After that, we go to 0, minus 45, 90, 90. Now you can see here there's two 90s together. And you can see here we put 92. So anytime you see 92, that means I have two plies that are stacked that are 90 degrees. And they're adjacent to each other. If I have 3, 93 instead, then I have 3 plies that are adjacent to each other that share the same ply orientation. Okay? Then after that, I have minus 45, 0, and 45. Okay, that's what I have. Now, You can see here, very interestingly, that I've separated every ply angle with a slash. Okay. And you can see here, for example, I have 45. That's ply number one. And then I have this slash and then zero. Well, this means I'm going to the next ply. So this is telling me where I'm going next. Now, in the case of the example we have 92. Yes, there is a ply between, there's obviously a delineation between two plies. But here, because they're the same angle, it's okay. It's customary to put them together. Okay. Another thing I want you to notice here is one more time. Just want to make sure this one goes against the tooling surface first. That's a convention used. Adjacent laminate of the same plier depicted by a numerical subscript. Each complete laminate is enclosed by a bracket. So if I'm done saying what the ply angles are, I'll just close it. And that means I'm done. Okay. When the ply stacking sequence is symmetric, say I have a symmetric ply stacking sequence. In those scenario, you put a subscript beneath, like that, after you're done mentioning the whole bracket. And you can see here clearly that 45, 0, minus 45, 90, 90, minus 45, 0, 45 is symmetric about that midplane there. And if I go here and look at what I have 45 first, I have 0 next, I have minus 45 next, and I'm going to the 90 one, so that's 90, and I only have 190. Then I close the bracket, and I have a symmetric there, S for symmetric. So that means that this gets mirrored. And you can see that there, 90 got mirrored there, minus 45 is there, 0 is here, and 45 is here. So you can see how everything got mirrored very nicely. We call those symmetric laminates. You can see them a lot in this area of expertise. Now, other types of situations you could have. You could have, for example, repetition. I have 45, 0, and suddenly I have minus 45, 90, and I want to repeat that 3 times. So instead of typing these 6 separate ply angles, I can just put them together like that. What that means is I have a ply of minus 45, 90 adjacent, repeated 3 times in that sequential order from bottom to top. Let's look at another example. When plies of fabric are used in a laminate, the angle of the fabric warp is used as a ply direction angle. So that's typically the convention used. Um, the fabric angle is enclosed in parentheses to identify the ply as a fabric. So not everybody does that. It's good practice. So if you put the parentheses, everybody knows now that that's a fabric. Otherwise, it's thought to be unidirectional. Now, in a lot of drawings, you're not going to see that parenthesis, so you have to really specify in drawing note what are really what are we really talking about. In this case, it's just fabrics. Everything's fabric, so you can probably get away with not using this parenthesis and just saying it all at once. I think it's better to have them so everything's clear. In this case, in this example, I have a 45, 0, 45, so that works. Um, Another approach you may see is you may write this. You may write 0, 45, 0 with an overbar top. What that means is that it's symmetric about the very last ply you drew there. But you have to write the word, you have to put symmetric here so people know. So that here will be equivalent to this. Okay. Um, but you could have a situation where you have unidirectionals, which is tapes, and fabrics, which is weave. And so in those cases, you want to use parentheses for sure. This one has no parentheses, so I know it's unidirectional, the 0, 1. So that's clear to me because I was very good at documenting what I've done. 45.0 minus 45.90 is something used quite extensively. Here you can see an overbar, and let's examine that a little more. You can see overbar here. So I have 45, which is fabric, 0 is unidirectional, minus 45 is next, fabric. Then I have 90, but 90 is not repeated twice, so it's only once. So that's why you have the overbar. And then we have to write the letter symmetric so people know that symmetric about the 90-degree ply. Usually it's known that that's the case because if I have an overbar, I should only have the overbar if I'm doing the symmetric condition. I believe it's better. I believe it's better to be very as precise as you can. I've seen so many problems in designs because people did not go and put the details necessary for the manufacturer or the technician to on the floor to know what needs to be done. Because things can go wrong during manufacturing. After you manufacture, it's good to take a tag and testing sample, and do a thermal depline. The thermal depline process, what it does is you heat up the sample and you remove the matrix material in order to look at the fiber orientations. That's a benefit of thermal depline. It gives you the ability to check everything. And I encourage you to check everything because there will be errors. In my experience, there will be errors and the design will suffer from those errors. And it's important to catch those early in the design process. Unidirectional 6-ply composites. You see a 6 there. That means there's 6 adjacent plies at 0 degrees. Cross-ply laminates, 0 and 90 ply angles. So I could have 0 90. If I have 0 90, that's cross-ply right there. Anytime I have cross-ply, I know it's 0 90. Then I have hybrid composites, which is a combination of different materials and systems. Then I have the angle plyometric. Okay, the angle plyometric. That one is going to be plus minus 45 across the board. And yeah, so that's what we have. And you can see symmetric here because about the mid surface, we have minus 45 is mirroring about the mid surface. You can see that there. Angle ply asymmetric is a situation where if this is plus, this is minus, but it's matching. And the fact that it's 45 makes it angle. So when anytime you see angle, that means 45s are involved. Balanced symmetric means balanced pairs exist anywhere in the ply second sequence. So minus 30 is balanced with plus 30. Minus 45 is balanced minus 45. Minus 60 is balanced with 60, and so forth. Antisymmetric laminates, minus 30, 60, minus 45, 45, minus 60, 30. So here you can see it's symmetric about here, but the signs are off. So we call it antisymmetric laminates. Off-axis layers is anything not 0, not 90 degrees. Very important nomenclature. In fact, let me pause for a couple of minutes so you can kind of look at this carefully. So let's look at micromechanics. The properties of unidirectional laminar is determined by volume fraction of constituent materials. So you have fiber matrix and you're going to have voids. So you have to really understand that before you can come up with the micromechanical properties. So I want to cover a few concepts here. I have the definition of volume, which is VI. And I can take values of either composite C, fiber F, matrix M. So the volume can be any of these ones here, VC, VM, VF. When you see a small v subscript I, that means volume fraction. That means I'm taking the volume of that particular constituent, ith constituent, and dividing that volume by the summation of basically the weight of the whole thing. So in this case, it's the composite, right? So that ratio I'm calling the volume fraction. What percentage I have of each material, really. Then I have the idea of weight. Weight is fairly straightforward as well. So I can take the weight as capital W and then lower capital W. And the weight fraction can be calculated as the weight of individual constituents divided by the summation of the whole thing or the whole composite. And that will give me the percentage of weight fraction for each of the pieces, each of the constituents. So we can use conservation mass. We know what that looks like. Conservation mass, so I have the weight of the composite equals the weight of the fiber plus the weight of the matrix. I can divide this equation by WC, and now I get the ratio of how much I have of the fiber, how much precision I have for the matrix. If we assume the composite is void-free, I can then take the void and not include it here. I have the volume of the fiber, volume of the matrix equals the volume of the composite. Divided by volume of the composite gives me these ratios. And notice how these ratios are the volume fraction that we talked about. So the fiber volume fraction plus the fiber volume and the matrix volume is going to give me 1 in this case, right? It has to give me 1. Okay, so then we have the density of the composite. So density of the composite, that's basically mass of the composite divided by the volume of the composite. But mass of the composite is the weight of the composite divided by the gravity. So I can leave G there. And now I know the weight of the composite is the weight of the fiber plus the weight of the matrix. Now further, I know the weight of the fiber is density. So what is the weight of the fiber? That's going to be mass of the fiber times gravity. And mass of the fiber is density times volume. So yeah, so that's what I have. And so also you can repeat that for the matrix. I get density of the matrix times the volume of the matrix. You can see here how the V ratio out, and that's very convenient. So I get that the density of the composite depends on the density of the individual constituents, but also depends on the percentages of how much I have of fiber and how much I have of the matrix. We can also write this equation in terms of weight fraction. You can see here at the bottom by treating it a little bit differently. So how you determine the void content in a composite material? So you have the experimental result. So you have the density via experimental results. That's going to be, I'm going to expand this equation here. I'm going to expand that and add the one for void fraction. So what is the theoretical calculation excluding void? So the theoretical calculation is going to be that I know the right-hand side very well. I know the contribution on the right-hand side, and I want to calculate V here. So if I know the left-hand side, um, if I know this, I know this, right? So I know all this. So you can see how the relationship. I may not know this, but I know this. I may not know this, but I know this. So I know the experimental value. I know the theoretical calculation. I can use this data to help me decide how much the volume fraction really is. So how you calculate void content? So the void content is going to be PCT, which is the theoretical density calculation here, minus experimental density calculation over here at the top. And you can see here when I subtract this to that, I'm subtracting this from that, and I get PCT VVF. Well, if I want to have just VV for the volume content, all I have to do is divide this equation by the density from the theoretical calculation. And when I do that, I'm able to then calculate the volume fraction for the void as one example, the void content, which is of high interest in determining the quality of the composites you landed with. A good void content problem is going to be, a good void content will be 1%. That's good composite. Less than 2 to 3%, it starts becoming bad composites. So let's look at an example. We have the burnout test of glass epoxy composite with the purpose of measuring void, the void fraction. You can also measure voids by taking a cross-sectional examination of a laminate. And trying to determine the area of voids you see and then extrapolating that to void calculation. But this is one of the methods that's used is the burnout test. You have the weight of the crucible, which is empty. The empty crucible is 47.6504. We then apply the composite. So now we have the weight of the crucible plus the composite. That's 50.1817. Then I will then have the weight of the crucible plus glass fibers at 49.4476. So that's important. Then I know the density of fiber and I know the density of the matrix because that comes from, it's provided, right? So it's provided, we can determine that from the spec, usually from the spec. And then I want to find the volume fraction of the voids if the experimental density of the composite is 1.86. So first I'll calculate the weight fraction, which is easy, is 49.4476 minus 47.6504. I have to remove the crucible weight out of this calculation, and I get 71% fiber weight fraction. Then for the matrix weight fraction, I just subtract 1 from here to get 0.29. So this, in this case, I have a 70-30 ratio, 70% the fibers, 30% the matrix. Then I have the density, the theoretical density. So what is that? So I can use the formula here. I plug everything in, and I get 1.902 grams per centimeter cubed. Okay. Then I can calculate the volume fraction. The volume fraction is 1.902 divided by 2.5. That's obvious. I know this, the density. I know the theoretical density, 1.902. I get 0.54. And for the matrix material, again, I repeat that, and I get 0.46. So I know now the volume fraction versus the matrix fraction. So now I know the theoretical value. I know the experimental value. Subtract the two, 1.902 minus 1.86 divided by 1.902, and I get a 2.21% void volume fraction, which is very useful so I know how much strength reduction I may expect from my manufacturing. If it's greater than 1.5%, you start to get poor quality issues. It doesn't mean it's bad material, but you have to qualify it to that bad, to the higher void volume fraction, if that makes sense. So typically, you can calculate the theoretical density of the composite because you know the theoretical value for the fiber and for the matrix. You know those, and you have those constituents, so you can check them to make sure that that's true. What that the spec says is correct. You can measure density of the fiber matrix. If you have the raw materials, you can measure them. So that's not the issue. The issue is when I put everything together. If I have voids, how do I measure that void percentage? And there's few methods are used, and this is one of the tests that people use. It's called a burnout test. Oh yeah, so micromechanics. So we have the longitudinal stiffness. So what are we talking about here? We have, you can see the fibers in this picture right there. That's a fiber. That means a different color pen. That's your fiber right there. And what we want to determine is what is E11. So I know the modulus of the fiber. I know the modulus of the matrix. I can measure that. But what is the modulus of the whole thing together? What is that? What is E11? Because I know the modulus of the fiber, I know the modulus of the matrix, but I want to know what is the modulus of the whole thing together. So the main equation to be using, and I show the derivations here. Um, It's very simple. So I know the strain in the one direction is the change in length divided by original length. This equation right here. So that's fairly simple. I know the stress in the fiber is going to be the modulus. So right, so if I'm straining this whole thing, then the fiber and the matrix will see the same strain in that direction. I hope so. So then the stress in the fiber is the modulus of the fiber times the strain, while the stress in the matrix is the modulus of the matrix times the strain. So we got that. That's clear. Now we know what is a load then? What is a load going through? So if I know the stress in the fiber times the cross-sectional area of the fiber plus the stress, and I'm looking at this equation now, plus the stress in the matrix times the area of the matrix, that should give me a total load. That should give me a total load there. So that also should be quite obvious what I'm doing there. So then I also have, if I substitute this equation 3.2, I substitute 3.2 into 3.3. I'll plug it in there. What I get is this equation here, right? Because I have EF epsilon 1, right? Sigma F is EF epsilon 1, EM, and stress in the matrix is EM times epsilon 1. So um, since the stress in the one direction is equal to E1 times epsilon 1, then I must have this. That has to be the case. There's no other way. But I know that if I do it per unit length, um, and I can fake it by multiplying by L here and L here, L here and L here, that instead I get volume quantities. And so what I really get is the fiber volume fraction now, and for the matrix and the fiber. So if I know, in other words, if I know how much I have, if I know the modulus of the fiber and I know the modulus of the matrix, if I know the fiber volume fraction, I should be able to tell you the modulus E11 with some, not perfect, but within 10 to 15%. It may not be perfect, but I can get there. And people have checked that with experiments, and you can see a plot here showing that it does follow that relationship. It does a fairly good job. In this case, you can see the plots being shown. We know the modulus of the boron. We know the modulus of the epoxy, which is in the 600,000 psi range. And if we know the volume fraction, which we can determine, of the matrix versus the fiber, I should be able to tell with not too bad the modulus of the whole system together of E11. When I say E11, what I'm talking about is the modulus globally when the fibers and the matrix are together mixed in. Okay, so that's a very simple formula that can be applied with some level of accuracy. Sometimes it's simple enough to just consider this term because this term tends to be smaller. So you can just look at that term and do a calculation. Typical fiber volume fraction can range between 60, 55% to 75%. So you can actually estimate typically what E11 is without having to do any test. Now, what about in the case of looking at E22? So earlier I was looking at unidirectional composite. I was asking this question. What is E11? That's E11. Now I'm asking, what is this one here? That's E22. So I'm loading it. So you're used to isotropic materials where the modulus is the same in all directions. But with composites, that's not the case. The modulus is going to vary depending upon which way you're looking. So E22 is across the transverse direction. And you can see here very clearly, this is a fiber again. And I'm going to use the same principles that I used here to calculate what's going on. And what you find after you derive everything is that this is the formula that gives you the modulus of the system. And what is this saying really? You know, it's saying that I have two springs, three springs in parallel. That's your matrix. That's your fiber. That's your matrix. So I have three springs in parallel, and that's what's causing the equations to look like I have an equation that looks like this. So again, if I have the modulus of the fiber, the matrix modulus, I know the volume fractions. I can get each to two with reasonable accuracy. Not perfect, but to some extent. And I have given you here, I invite you to pause it here and look at this carefully. It's not very complicated. It's just the same process we used here, but now we have the matrix and fiber in parallel. There's other calculations that can be done to estimate shear modulus. If you know the shear modulus of the fiber and the matrix, you can calculate the fiber and you know the fiber volume fraction, you can calculate the shear modulus. Um, and these are the formulas you're going to see out there. Poisson ratio also can be done in that manner. In a lot of applications, you may not have the shear modulus of the constituent materials, but you could use, the modulus of the fiber, the Poisson ratio of the fiber, so you can estimate what the shear modulus is of the fiber or the matrix. So we conclude here, very top level, how to estimate micromechanics properties, and we'll start stepping into some of the theoretical understandings of this material. I thank you for listening today.